Hi, my name is WonJOON and I'm a student participating in Summer 2020 Texas A&M's O-REU program. I'm currently a rising senior studying materials engineering and minoring in computer science at the University of Illinois at Urbana-Champaign. Today I'll present about my project, Parametric Finite Element Analysis of Shape Memory Alloy Actuators. Before I begin, I would like to thank the project sponsors, NASA ULI and Texas A&M University, and my mentors, Dr. Lagudas and Dr. Karakulas, for their help. Noise pollution can cause various health problems ranging from poor concentration to a cardiovascular disease. Especially, supersonic aircraft can cause huge noise pollution during their overland flight due to their sonic boom. The goal of adaptive aerostructures for revolutionary civil supersonic transportation, the NASA ULI project that I'm a part of, is to meet the noise requirements for overland flight for commercial supersonic aircraft by developing innovative design approaches with embedded shape memory alloy SMA actuators. The structural adjustment of the aircraft using SMA actuators enable the noise reduction. My role in the project is to perform parametric finite element studies to assess the influence of key characteristics of various SMA actuator forms. Here is a quick review for people that are not familiar with shape memory alloys. Shape memory alloy is a type of material that can recover their original shape when heated after being mechanically deformed. The unique property of SMA is attributed to the phase transformation between the low temperature martensite phase and high temperature austenite phase. This property, along with its high energy density, makes SMA a very useful actuator element in industry. The image on the right shows the use of SMA ribbon actuator in aircraft's chevron for noise reduction. Here are the main goals of my project. First, I'll design the parametric models of various forms of actuators including wire, bar, torque tube, and spring actuators using Python. Then, I'll use user material subroutine of Abacus to simulate the SMA performance of the models and study how different input variables affect the SMA actuator performance. The images below are the parametric models that I built. They have various functions including partitions and geometry sets that are very useful for efficient meshing. Here are some design specifications for the actuators that fit the NASA ULI requirements. As shown on the slide, I tested bar and cylinder under uni-axial load with minimum target stroke of 3 inches at different maximum internal stress values. Also, I measured the linear displacement of torque tube under different stress values as well. For this presentation, I'll focus on simulation with maximum stress value of 100 megapascal. Having a good mesh shape and density is very important to get accurate results from finite element analysis in an efficient manner. The optimal mesh density can be found by conducting same simulations multiple times with increasing mesh density until the result converges, and this process is called Convergence Study. This slide shows the example of Convergence Study result for the torque tube simulation. The stress and strain data were extracted from the highlighted finite element at the clamped end of the torque tube, as shown in the figure. The graph on the right shows the maximum shear stress at different mesh densities. The bar graph shows the actual shear stress values, and the black line graph shows the percent difference in the values. Usually the percent difference less than 5% is considered safe, thus the optimal mesh density is 5 in this case. Convergence study for other types of actuators were also conducted in a similar manner. Here are some results of the simulations. The colored contour plot shows the martensite volume fraction of the SMA bar. The phase toward negative z direction was fixed, and the phase toward positive z direction was pulled in z direction using continuum distributing coupling and concentrated force to apply uni-axial tensile load. As shown in the video, the SMA bar was first loaded to develop an internal stress of 100 megapascal, cooled down to martensite phase, and went through the complete phase transformation to go back to austenite phase. The graph on the right shows the displacement of the free end of the bar and the martensite volume fraction of the bar throughout the total simulation time of 90 seconds. The dimension of the bar is shown in the table. This slide shows the result of the similar simulation with a SMA wire instead of a bar actuator. As shown in the table, this cylinder actuator could meet the target stroke of minimum 3 inches, which is equal to 0.0762 meters. This video shows the simulation of the torque tube that is loaded to develop an internal stress of 100 megapascal and went through isobaric thermal cycle. Again, the face toward negative z direction was fixed, and the face toward the positive z direction was rotated by using kinematic coupling and applying a moment. The graph on the right shows the angle of rotation and martensite volume fraction throughout the simulation. The dimension of the tube is shown in the table below, and this dimension was provided by Dr. Calculus as one of the realistic SMA torque tube dimensions that can be used for aircraft shape morphing. The rotation of the tube was converted to the linear displacement of 0.0183 meter. In the process of designing SMA actuators that fit the NASA ULI design specifications, many interesting relationships between different input variables and SMA actuator performance were found. In this case, SMA bar and torque tube actuators of different lengths were loaded to the same internal stress level of 100 megapascal and was thermally activated to test the correlation between the length and the performance. As shown on the graph and the table, the displacement increased with the increase in length and the amount of change seems fairly consistent. The table shows the actual displacement values of the SMA actuators at different lengths. This graph shows the performance of SMA actuators of different lengths that was shown in the previous slide. As shown here, the performance and the length of the actuators are showing linear relationship. In this case, SMA bars and wire that have different cross-sectional shape and area were loaded to find the correlation between the shape and performance of the actuator under uni-axial load. The images on the bottom shows the cross-section of each SMA actuator on the top. As shown in the video, the amount of deformation stroke seems almost identical for all three of them. The graph shows the displacement of the free end of different actuators that is shown in the video in previous slide. And the table shows the actual values of the displacement. As shown in the graph and the table, the values are very similar with difference less than 5%, and this difference can be attributed to the fluctuation in finite element analysis. From this result, we can conclude that as long as the amount of stress and the length of the actuator stays consistent, the displacement will be the same. In this case, the different types of SMA actuators, bar, wire, and torque tube were loaded to different stress levels of 100, 200, and 300 megapascals to check the correlation between the stress and the stroke. As we can see, all three graphs shows the increasing stroke with increasing stress. However, the amount of change is decreasing. The result from the previous slide can be explained by this reference, maximum transformation strain versus applied stress graph. As shown here, the graph shows the exponential fit, and as the stress level goes higher, the transformation strain converges. This graph can also be used to explain the linear relationship between the SMA actuator length and its deformation. If the transformation strain is only related to the stress, strain values should be identical when the amount of applied stress stays constant. In this case, the correlation between the stress and the phase transformation temperature of uni-axial stress and shear stress was measured. All four major transformation temperatures are showing a trend of increasing temperature with increasing applied stress. The result from the previous slide can be explained by this reference, stress versus temperature plot for SMA material. We can see that the SMA is in martensite phase at low temperature and austenite phase at high temperature. Also, we can see the trend of increasing transformation temperature with increasing stress that we observed in the previous slide. There are still some ongoing simulations about SMA springs. The videos on this slide show examples of the spring under different types of loading. In case of the spring simulations, different parts of the spring goes through different type of loading including shear, compression, and tensile loading at the same time, so it requires more thoughtful analysis of the data. Here is the conclusion of my project. First, I was able to successfully design the parametric models of different forms of SMA actuators with many useful functions including partitions and geometry sets for efficient meshing. Also, I was able to design the SMA actuators that fit the NASA ULI design specifications. My results are the outcome of the preliminary analysis, and the exact size of the actuator will be determined after considering their implementation in the host structure. Finally, I was able to find many correlations between various input variables and actuator performance of SMA bar, wire, and torque tube under different types of loading. Throughout the Texas A&M's O-REU program, I was able to get knowledge in shape memory alloy and proficiency in finite element analysis simulations. Thank you again for providing me with this great research opportunity, and thank you for listening.